Now let us go through a kind of a real life-like examples of the general theory. And so here we are going to set up a system of differential equations that models a population of ants, aphids, and ladybirds. So we're going to measure time in days and population in kilograms of biomass, or whatever, grams. I'm not going to fit it into data. I'll just invent some specific numbers for the sake of the story. And the assumption here is that the ladybirds, they eat aphids, which is true, actually. And at first, we assume that ants and aphids, they have a source of food not included in the model. So ants eat something, aphids eat something, but the importance, maybe you need to have some background. So the important part is that ladybirds, they eat aphids, but ants, they protect aphids from ladybirds, and they kind of milk aphids, and they eat their milk. So to aphids to ants is something like cows to people, and ladybirds may be thought of something as leopards. So leopards would eat cattle, and humans try to protect cattle. The same type of a relation here. Okay. So since ants have an external source of food, it means that the equation for x prime is going to have a positive x term. So the more population is, the faster it grows. And same for aphids. But then it is given here that ladybirds only eat aphids. So which means that without aphids, they would die out. They will go extinct. So that's why the equation for ladybirds is going to have a negative z term, because on its own, the population is going to disappear. So on its own, the rate of change, the growth rate, is negative. And then, of course, if we have a negative z term, then, in the logistic equation, so usually there is the positive x term and the negative x squared term, but here the negative z squared term is not necessary because the z term is already negative. So for the ladybirds, we are not going to have minus z squared. Okay, so here is a reasonable system. So why is it reasonable? So these are ants. X are ants. And so notice the following. So notice that without any other variables, so if say y is 0 and z is 0, we would have a logistic differential equation here. For small populations of x, the growth rate is proportional to the population, but for large populations, it is bounded by restricted resources. But besides, we have this extra term that tells us that if the population of aphids, y, is positive, so the second equation is for aphids. If the population of aphids is positive, then it makes the growth rate, the rate of change of ants, faster. So then the population of ants is increasing faster. And this is because aphids provide an extra source of food. And the idea here is that it is proportional to the product of the population, which is interpreted something like as follows. Suppose that X is the total population of ants, Y is the total population of aphids, then the product x times y is proportional to the probability that an ant meets an aphid. And such an encounter is good for them. So which means that every time such an encounter happens, the ants are going to get more food, and then they're going to reproduce faster. All right, I hope it's clear. So now let us look at the equation for aphids. So first, if the other two terms are missing, if without y or z, if we just look at the equation on y prime, then again it is a logistic differential equation, which means that aphids on its own, in the beginning when the population is small, the growth rate is proportional to the population, but as it grows bigger, the growth rate starts to slow down, and then eventually it stabilizes and the growth rate becomes 0 and the population stabilizes. So now then we have a positive term with xy, and again the idea here is that x is the ant population, aphid is the y is the aphid population, so whenever they meet, this encounter is beneficial for aphids too, because ants are going to take care of aphids, and they're going to protect aphids from ladybirds. That's why here we have a positive number, right? So the fact that this number is positive and this number is positive, this is because whenever ants and aphids meet, this encounter is beneficial for both of them, because ants care for aphids and aphids provide food for ants. But here we have a negative term. So what does it tell us? So y is the population of aphids and z is the population of ladybirds. So this term kind of shows is proportional to the probability that an aphid meets a ladybird. And of course, if an aphid meets a ladybird, then the ladybird eats the aphid. So this is bad for the aphid population. Hence the negative term. This is linked to this story when ladybird eats aphid. Alright, and now if we look at the population, the equation for ladybirds, which is the last one, z prime, then on its own, ladybirds would die out, would disappear, so which is given by the fact that the growth rate is proportional to the population with a negative coefficient. But whenever they meet aphids, this is beneficial for them because aphid is their source of food. And then you could try to calculate the intrinsic carrying capacity of the ant population, which means you would have to rewrite this. And apparently this is x prime equals 0.2x, which is taken out, and then whatever this is 1 minus x over 200. I guess it is true. Yeah. And same thing here. If you try to rewrite this in the logistic form, then this would be y prime equals 0.3y. Then we take out 0.3 times 1 minus y over 150. So which means that 150 is the carrying capacity of the aphid population. Of course, these numbers are just made up, so I just wanted some specific numbers to explain the logic of the model. So in practice, if you wanted to apply this in practice, then these would be parameters that you would try to feed the data. But I don't, of course, I don't have any real data on ant population or aphid population. So, well, but then, so notice that here we have this negative term, but at the same time, note that it may not be necessary because ladybirds already limit the aphid population. So the significance of this negative term is to prevent the theoretical aphid population from the model to grow unboundedly. But because of this negative term, it's not going to grow unboundedly anyway in the presence of ladybirds. So that's why this negative y² term might not be necessary. So another thing is that how we can change it is that, for example, here we assume that ants have an extra source of food, but at the same time we already have a positive term. So which means that the ants are not going to die out anyway, because ladybirds do not eat ants, and ants, they benefit from just having aphids around. So if we have a positive population of aphids, then we have a positive term, positive growth rate for ants. So we may not need this positive term in the positive linear terms, so it may be negative. We don't know, but what I want to say is that there are several models here, and of course the logic behind each one of them is reasonable, and which model is more precise, you can only test it by trying to solve each model and compare it against some real data. Well, of course, here it is a bit theoretical, because getting real data on ant population or ladybird population is very challenging. I don't think it is possible. But at the same time, the same logic behind the model, so instead of ants and ladybirds, you can think of feelings of two individuals towards each other. So that's Rinaldi's model. So then the logic here would be that on its own, feelings disappear, but with the presence of your love passion, feelings would grow. That's a reasonable interpretation. Or, for example, instead of feelings of several individuals towards each other, you can think of a business competition. So if X, Y, and Z is the market share of certain products like, I don't know, iPhone, Android, and Windows Phone, then negative coefficients at the product mean a business competition, right? And positive coefficient here means adoption rate, and so on. So you can try to interpret it like this, and then you would have some real data that you can verify the model against. But I think it's just the simplest way to explain it is in terms of species competition.